start. So today we want to discuss about electronics. So we can have a model of a phone because it is an electronic device. Then from there we know that it is electronics. It is based on the discussion on semiconductors. And that's why I have a product of a semiconductor here. Then you know this one is obtained from the atom, and that's why I have an atomic structure. So the students I can explain about the nucleus, the atoms, the nucleons, then the energy levels, so that we interact with the two atoms, we see how they split and they form the different different bands. And again we move ahead to see how we can be able now to look at the relationship, the interband theories, the optical, the electrical, and the magnetic properties of these materials. I think those materials can help the students understand more about the electronics. Yes, that's what we will be able to teach today.
Thank you.
So we can proceed to the class.
Yes, good afternoon, class. Good afternoon. How are you? Yeah, so today we want to have our lesson in a different style. So the last time we met, we were discussing about radioactivity. We have looked at the definition of radioactivity as a subject, as a topic. We did look at the types of radiation emitted when an atom undergoes radioactivity. So we have seen those alpha particles, the beta radiations. We have also seen the alpha, the gamma radiations. Then we looked at the ionizing effect, the penetration power. We went ahead and looked at the decay series, the half-life, and then of course we looked at the applications of radioactivity. So today we have another topic, and that topic is related to radioactivity. So we want to look at electronics. So when you talk about electronics as a topic, now what comes into your mind when you talk about electronics? What do you think, Jeremy? When you talk about electronics, what comes into your mind? Electronic devices such as a phone, Emmanuel, computer, Mugo, television, Samuel, laptops. So those are electronics devices. And these electronic devices have components, and those components are the things that we are going to discuss today. So in our day-to-day life, we interact with these electronic devices, and these electronic devices have integrated circuits. And those integrated circuits now have electronic components. So this topic is very interesting. It is based on the discussion of these components, especially the semiconductors, so that we can be able to see how these semiconductors are able to work inside the electronic devices. So when we talk about electronics, the functioning of these components such as the diode and the integrated circuit is based on the behavior of some materials. And an example of that such a material is a semiconductor. And the common examples of semiconductors that we know, which semiconductor do you know? Yes, we have silicon, and another one is germanium. Those are the two types of semiconductors that we shall discuss today. So in this topic, the electrical conductivity of the conductors, semiconductors, and insulators is explained further using what we call the energy band theory. The energy band theory. Now, in front of you here, we have a model. Which model is this? This is the model of an. Now, from the atom, we are going now to understand more about the energy band theory. So, according to this theory, you realize that an atomic structure reveals that we have electrons. So you can see electrons here. So in an atom, we have the nucleus. The nucleus has subatomic particles we have, what do we have in the nucleus? We have the protons and the neutrons. So these protons and the neutrons have a name. Tunasitaje? How do we call them? Yeah, we call them the nucleons. Then we have the other subatomic particles that are the electrons. And those electrons now are moving around the nucleus. Now, when we talk about the energy band theory, according to this energy band theory, when two or more atoms are brought closer to each other. So I have an atom here, I have another one here, and I also have another one here, and another one here. So when two or more, so at least I have how many? How many do I have? Okay, well, you can see one. You can also see one. Then you share with your neighbor. Then from there, I can remain with these two. So when you look at this atom, it has the nucleus. So you can see the nucleus. So inside this nucleus, we have the nucleons. Tumesema we have the protons and neutrons. Then we have the electrons that are moving around the nucleus. So we are saying that when two or more of such atoms interact, because of the magnetic properties or the electrical properties of those materials, this atom is going to split. And when it splits, the energy levels now split into bands. So, yeah. So, looking at this atom, we have the nucleus, we have the first energy level, the second energy level, and the third energy level. Can you help me with a pen so that I can use it here? So this is our atom. So we have the nucleus, the first energy level, the second one, the third. So inside the atom we have the nucleus. So in the nucleus we have what? Protons and neutrons. So our first energy level we are going to give it letter K. The other one is what? This one is M. And the other one is M. So those are the three energy levels. So when these atoms now interact, two or more, we are saying that these energy levels will split into bands. So we start with now can we name the energy levels? Which is the first occupied energy level? In chemistry we discussed that. The first one is K, because it is closer to the nucleus. Now, what do you understand about the energy level that is closer to the nucleus? What about the forces of attraction? Yeah, because the nucleus has protons that are positively charged, and we have electrons that are moving around that nucleus, and the electrons are negatively charged. So because of the electrostatic forces of attraction, this energy level is highly attracted to the nucleus as compared to the second and the third energy level. Even if we add the fifth one. So the fifth one will be weakly attracted to the nucleus because of the electrostatic forces of attraction. And that determines now how the energy level is going to split. So you start with K. Because it is very closer, it is going to split to how many bands? how many bands? It is going to split once. So we have a band there. Come to L. It will split to how many bands? 3. So it will split into 3 bands. What about M? What about M? Yeah, M now will split into 4 bands. Yeah. So that is what we have. Now, when we talk about electronics, we have 2 important bands. Which one and which one? Which one and which one? Samuel, the most important bands in electronics. We have the valence band and the conduction band. And the conduction band. So now the interband energies. So the interaction and the interband energies will now determine the electrical, the optical properties of a material. So you realize that the outermost energy level containing the valence electrons splits more easily into many bands than the inner levels, and I've explained that it is because of the strong forces of attraction. So the splitting of the energy levels into bands and the interband distances will dictate the electrical, optical, and the magnetic properties of a given material. So you realize that now between the conduction band and the valence band, because we have identified those as the most important bands in electronics, we are saying that we have a gap, and that gap we call it the forbidden energy gap. So yeah, so we have a gap there between the conduction band and the valence band. So you are going to realize later, as we discuss, that this gap will determine whether a material is a conductor, an insulator, or So when we discuss that, now you can see how the semiconductors came to being. So when we talk about that energy gap, it is important now we discuss about those materials, and we shall begin with the conductors. I want to begin with the conductors. So we have said that these materials are already split into bands. Now, when you talk about a conductor, it is going to have those two bands. So we are going to have the valence band, and then we are going to have the conduction band. But for the conductor, you are going to realize that the conduction band and the valence band, they are overlapping. So for the conductor, the valence band and the conduction band are overlapping. That means there is no energy gap between the valence band and the conduction band. So the valence band will be containing the valence electrons. The conduction band will be containing the conduction electrons. So when you increase the temperature of that material, what happens to the atoms making that material? What happens to the atoms that are making that material? The vibration of these atoms will start increasing with an increase in the temperature. And because for this material to conduct, the conduction electrons must move from the valence band to the conduction band. And there is these particles that are vibrating randomly in that material. What will happen? They will oppose that flow of electrons. And that's why we say that for conductors, an increase in temperature, that's what with the resistance of that conductor. Yeah, an increase in temperature increases the resistance of the conductor. So the key points that you need to understand from this material is that for conductors, the valence band and the conduction band, those bands are overlapping. They overlap each other. So there is no energy gap in between. And an increase in temperature leads to an increase in the resistance of the conductor. Tuko pamoja? Good. Now, I want us to look at another material. That is the insulator. We look at the insulator. And when you talk about the insulator, under normal circumstances or conditions, there exists a very large energy gap between the conduction band and the valence band. So if we can have a diagram of an insulator, so we are going to have the three bands. So we have the valence band, we have the energy gap, then we have the conduction band. And we are saying that if this one is our conduction band, so this one here is what we call the energy gap, and this one here becomes our valence band. So we have the conduction electrons there, we have the valence electrons there, then at this other side, what we have is what? Now we have an energy gap. Another name for that gap is a depletion layer, something that does not have anything. Yeah, an energy gap. I don't know whether it was discovered from the forbidden fruit. That one I don't know. But this one has been forbidden by the electrons. No electron wants to survive there. There is a gap. See there? Yeah. So we have the conduction band, we have the valence band. So for this material to conduct, what must you do? You must rise the temperature of this material so that you excite these electrons, they gain some kinetic energy, they get dislodged. Mugo, they get dislodged. Yeah. And when they get dislodged, what happens? They can be ejected so that they move to the conduction band. So where it will create a gap, another electron will come and join there. But for an insulator, a lot of energy is required. So you will continue heating, so there is no amount of heat that will excite an electron for it to move from the valence band to the conduction band, because you will end up breaking the material. And that's why you realize that the electron is tightly bound in the valence bond, and it requires a very large amount to dislodge it from the parent atom and make it cross the forbidden gap. And on the other hand, this amount of energy that is supplied is going to break down the crystal. And the absence of electrons in the conduction band makes this material to become a poor conductor. And that's why insulators don't conduct. Yeah, insulators are always poor conductor. Yeah, they are always poor conductors. So the absence of electrons in the conduction band renders a material a poor electrical conductor. So an increase in temperature or addition of impurities, because it is in this topic that an impurity is a good material. So you add an impurity, you cannot make it a conductor. So that has no effect on the conductivity of the material. So in general, we are saying that an increase in temperature does not interfere, has no effect on the conductivity of the material. So an increase in temperature has no effect on the conductivity of the material. You see, when I'm saying that this one is not a good conductor, it does not make it useless, because an insulator is as good as a conductor. Because you cannot have a conductor and you forget about the insulator, because you need to protect that conductor against those electrons getting out of the conductor. See, you also need to protect yourself, because we know that the current you can experience an electric shock if you touch an open conductor. So the insulator is going to help us in insulating that material that we are calling a good conductor. So it is as important as the conductor. So as we say that it is a poor conductor, it does not make it useless. So we go to the third material that we call a semiconductor. A semiconductor. So same as the insulator, we are going to have the 3 bands. So this one will be our conduction band, our CP. This one will be our valence band. Then we have a gap there. We call it a forbidden gap. Or sometimes I said we can use a depletion layer. So you realize that this one, we say, for the insulator, we say that it has a wider, because we want to compare. Senor, for this one, we are going to say that it has a narrow forbidden gap. And for that reason, you realize that if you increase now the temperature of that material, that electron that is strongly bound in that material will gain some kinetic energy. And finally, that electron is going, as it is excited, it will be dislodged from the material. So this electron will move to the conduction band. Where this electron has left, it is creating a gap. So another electron will still move to do what? To fill that gap. So you realize that eventually we are going to have electrons flowing in the valence band. We also have them flowing in the conduction band. So what we are trying to say is that the energy band diagram for a semiconductor has 3 parts. We have the conduction band, we have the forbidden gap, and then we have the valence band. But when you look at that forbidden gap, it is smaller as compared to that of the insulator. Yeah, it is smaller as compared to that of the insulator. And the conduction band has almost no electrons. It is completely empty. While the valence band is almost completely full. And that's why we are saying that we must come up with a way of moving those electrons from the valence band to the conduction band. And then you are going to realize that we can only do that if we increase the surrounding temperature of such a material. So you realize that if you increase the temperature, you offer a chance of that electron now to move from the valence band to the conduction band. So where we are, an electron has left, what happens there? It creates a gap. Which gap is created when an electron moves? We call it a hole. Sindio? Yeah, so an electron will move and that electron will create a gap. So that gap is known as a hole. So another electron, now that hole has another name. Deficient of electrons. They have deficient of vitamin C. And they are taken outside to have some basking of the sun. Yeah, so that hole now we say that it has deficiency of electron. It is scarcity for an electron. So another electron will come and fill that hole. The electron will move to the conduction band. So eventually, you are going to realize that in the conduction band, which was initially empty, has now some electrons flowing there. And for the valence band, we are remaining with what? We are remaining with what? We are remaining with several holes. So the movement of electrons will constitute what we call electron current. The movement of holes, it is going to constitute what we call hole. It is hole current. So we are saying that for the semiconductors, the movement of these holes and the movement of electrons will make that material to become a good conductor. And eventually, total current flow in semiconductors is therefore due to the flow of electrons and holes, and the electrical resistance of semiconductors thus reduces when the temperature increases. So we are going to say that an increase in temperature leads to a decrease in resistance. We can also say that an increase in temperature improves the conductivity of that material. So those are the components that we were to discuss. So we have looked at the conductors, we have looked at the insulators, and we have already looked at the semiconductors. So we have been able to derive this semiconductor. So you can see the common parameter there, the physical property that we are considering in these three materials is the temperature. So for the conductors, we have noted that temperature has an effect. Is it a positive or a negative effect? It is a negative effect because an increase in temperature reduces the conductivity of a conductor. Yeah, because of the collision of the electrons and the atoms of this conductor. We have also noted that temperature has no effect on an insulator. See that one we have seen? We have also discovered that temperature is a very important factor as far as a semiconductor is concerned. Yeah, so an increase in temperature for semiconductors is going now to lead to an increase in conductivity because it provides that energy, the energy required for the electron to move from the valence band to the conduction band. And we have also discovered that in the valence band, the movement of an electron creates a hole. So that hole, it is the division of electrons. So another electron will be able to come and fill that hole. And where that electron is living is also creating another hole. So in the valence band, we have the movement of holes. And that constitutes what we call the hole current. In the conduction band, now that the electrons have arrived, they are moving there. And they constitute what we call the electron current. Yeah, and that electron current now is an impure semiconductor. We have added an impurity. And the reason why we are adding an impurity is to improve the conductivity. Yeah, so that is what we shall discuss in our next lesson. So I want you to go and do more research about intrinsic and extrinsic semiconductors. You go further. For the extrinsic semiconductors, they can also be divided into P and N type. So as we get our free time, I want you to look at that, and that is what we shall do in our next lesson. Any question up to that point? Is there any question? Anywhere you do not understand, you need clarification? Have you enjoyed the lesson? Yes. Yeah, you can clap for me. Teaching and mentorship. Oh, Njiiri, we are free to serve. Njiiri, God is the great heart, and I will sing.